Hey everyone, welcome to The Explainer. For week 2, we are diving deep into routing concepts and RIP. I'm going to be your IT mentor today, and we are going to completely demystify exactly how data finds its way across complex networks. Seriously, if you've ever wondered how a tiny packet gets from your device to a server halfway across the globe without getting hopelessly lost, you are absolutely in the right place. So let's just dive right in. Here is our roadmap for today. We've got 1. Static versus dynamic routing. 2. Trust, distance, and convergence. 3. Understanding RIP versions. 4. Timers and loop prevention. And 5. Configuring and verifying RIP.
All right, Section 1, static versus dynamic routing.
So the very first major hurdle in networking is honestly pretty basic. How do we actually teach our routers where to send the data? I mean, they don't just inherently know the layout of the entire internet, right? We basically have 2 totally different philosophies to handle this. On one side, we have static routing. This is manual. It's completely fixed. You tell the router exactly which way to go, and it literally never deviates. Even if a cable gets cut, it just doesn't adapt. But on the other side, we have dynamic routing. Think of this like a live GPS for your network. Routers use protocols like RIP, EIGRP, or OSPF to automatically exchange information with each other all the time. If traffic conditions change or a link suddenly goes down, dynamic routing adapts instantly on the fly to find you a brand new path.
Moving on to Section 2, trust, distance, and convergence.
Now, when routers use these dynamic protocols to talk to each other, they get flooded with all sorts of different route suggestions. They need a highly reliable way to pick the absolute best path among multiple options. So how do they decide who to trust? Well, they do this through something called administrative distance, or AD. You can think of AD as a trust score, kind of like a Yelp rating for network routes. But here's the catch. In this system, a lower score is actually way better. A directly connected interface has an AD of 0. It's undeniably true, right? A static route, because a human explicitly configured it, gets an AD of 1. But RIP? RIP has an AD of 120, which perfectly explains why, if a router has a manually configured static route and a dynamically learned RIP route pointing to the exact same destination, the static route is always going to win. It's just trusted more.
But what happens when things actually go wrong? Let's talk about convergence. Convergence is essentially the state where all the routers in a network finally have consistent and accurate routing tables after some kind of change happens. Imagine a vital network link suddenly fails. Boom. All the routers need to scramble, figure out the new path, and update their tables. And this needs to happen fast. But here's the reality check. RIP is, it's a slower protocol. It can take up to 180 seconds to fully converge. And honestly, in internet time, 180 seconds of your network being completely confused is basically an eternity. This is exactly why network stability heavily depends on you understanding these protocol limits.
Which brings us to Section 3, understanding RIP versions.
To really get the mechanics of RIP, we have to know it's a distance vector protocol. That means it doesn't look at bandwidth or traffic delays to find the best route. It simply counts the hops, literally just the number of routers, between the source and the destination. And this brings us to a magic number, 15. RIP has a hard, built-in limit of exactly 15 hops. If a packet needs to go through 16 routers to reach its destination, RIP basically just throws its hands up. Asking to go 16 hops in RIP is the ultimate, are we there yet? Because as far as the protocol is concerned, at 16 hops, that destination is considered completely unreachable. No way, no how. Now, not all versions of RIP are created equal. RIP version 1 is the older, much more rigid protocol. We call it classful, meaning it absolutely does not support sending subnet information along with its routing updates. It just assumes standard network sizes. But RIP version 2, that is our modern standard. It is classless. That means it supports variable length subnet masks, or VLSM, and super crucially, it supports route authentication. Today, you are almost exclusively going to see RIP v2 out in the wild because it brings that much-needed flexibility and security to the table. And speaking of flexibility, one of the biggest upgrades in RIP v2 is the ability to just turn off auto summary. See, RIP v1 automatically summarizes your subnets to their default class boundaries, whether you want to or not. But if you have subnetted networks split across different physical segments, what we call discontiguous networks, auto summary is going to route traffic to completely the wrong places. It's a mess. So using the command no auto summary in RIP v2 is an absolute lifesaver that ensures your routing actually remains perfectly accurate.
All right, Section 4, timers and loop prevention.
So we've talked about how RIP finds paths, right? But how does it clean up dead routes without accidentally creating these chaotic, endless traffic loops? Well, it relies on a very specific set of timers to manage a route's lifecycle. Let's walk through the whole shebang. Every 30 seconds, the update timer triggers, and routers cheerfully share their tables. But if a route isn't updated for 180 seconds, the invalid timer hits, and the route is officially marked dead. Right at that same moment, a 180-second hold-down timer kicks in. This essentially suppresses any new, potentially false updates about that route from messing things up. And finally, at the dramatic 240-second mark, the flush timer expires, and that dead route is permanently, literally, scrubbed from the routing table.
Now, you combine those timers with these three really clever mechanisms, and you get RIP's loop prevention. First, split horizon. This makes sure a router never, ever advertises a route back out the exact same interface it learned it from. It just makes sense. Second is route poisoning. This actively advertises a failing route with an unreachable metric, basically shouting a warning to the other routers immediately. And third, we already saw those hold-down timers, freezing updates while the network stabilizes. Working together, these three ensure that incorrect routing info doesn't just endlessly bounce around your network forever.
And finally, Section 5, Configuring and Verifying RIP. Okay, so we know the theory, but let's actually build this together on the Cisco command line. Getting a modern RIP setup running really only takes these 4 simple commands. Think of this as your quick server room cheat sheet. First up, you type router RIP to jump right into the configuration mode. Second, you dictate the protocol with version 2. Third, you drop in that absolute lifesaver command we talked about, no auto summary to prevent routing errors. And lastly, you use the network command followed by your network address to actually start advertising your connected networks out to the other routers. Super straightforward.
But look, as any good IT mentor is going to tell you, configuring it is really only half the job. You absolutely have to verify your handiwork. Show IP protocols is your go-to for verifying your timers and versions. Show IP route lets you look right at the live routing table to see if your RIP routes actually made it. And then there's debug IP RIP. This one shows you live routing updates exactly as they happen. But hey, I'm warning you right now. Use this live debug command with extreme caution on a production network, or you might totally overwhelm your router's processor.
And that brings us to our final thought for this explainer. We've seen exactly how RIP works, how it completely relies on hop counts, and how those timers function. But I really want to leave you with this question. Is RIP simplicity actually worth its slower 180-second convergence speed in a modern network? I highly challenge you to take this question into your next packet tracer assignment. Build a multi-router network, introduce a link failure, watch how RIP adapts, and then see if your curiosity leads you to compare it against faster, more complex protocols like OSPF. Thank you so much for joining me today, and definitely keep experimenting out there.